Hi, and welcome to my presentation for Mine 853. My name is Ryan Anderson, and the topic I chose to do for my term project is a very low frequency transmitter-based GPS-style underground positioning system. This is something that was put forward by Greg Baiden in 2009, and he had a patent on it. And I thought it was an interesting system, and it seems plausible that it could work, and it's something that could be very useful for underground autonomous mining if it's feasible. So I decided to investigate it and do some basic simulations to see what kind of feasibility it has. So the motivation for underground navigation is really mining automation. So you can figure out where things are underground with classical surveying techniques, but if you want to have any kind of automated vehicles underground, they need to have on-the-fly accurate positioning so that they know where they are relative to other vehicles, people, and in the mine itself. So on mining automation, Rio Tinto, for example, has now moved over 100 million tons of rock on the surface in automated hauling vehicles, and they're really pushing for what they call the mine of the future, quote unquote. So within big businesses and big mining companies, there really is a push towards more mining automation. But as I said before, this all requires some kind of position tracking. So on the surface, this is easy. You can do it with GPS. But for underground navigation, there really hasn't been like a killer solution to the navigation problem. So you're forced to look into alternatives that don't rely on GPS. Although really getting something that functions the same as GPS would be the gold standard and is ideally what you would aim for. So we'll look at the competing technology. The main competing technologies for underground navigation are inertial tracking, and that orange block is an example of a MEMS-based inertial navigation unit. So these work by measuring acceleration and angular rates with accelerometers and gyroscopes, and performing tracking by dead reckoning. So you're just integrating acceleration and angular rates to get position and orientation. It's also what I'm calling here radio signal-based tracking, but really this just means using megahertz frequency transmitter devices. So this is tracking by having RFID tags throughout the mine, or Wi-Fi hotspots, or Zigbee, for example. So that's very similar to the project we did in class. You can also have navigation by mapping. So this is having something like 3D laser scanners on the vehicle that map the walls of where they are, and from that determine where they are, so you'd have a pre-built map that they're comparing themselves to. And also there's actually been some research into using purely magnetic tracking, where magnetic fields are generated, and by measuring the magnetic fields at a certain position, you can figure out where you are. So this is sort of typical tracking accuracy you'd see from other results. So for purely inertial tracking, really, there's not much positional accuracy to talk about, especially for anything MEMS-based, so small and relatively cheap and low power. You accumulate drift much too quickly for it to really be useful. So all the research that you see on inertial tracking and all the implementations nearly always combine it with some other form of tracking. So, for example, GPS, or they'll have speedometers and that kind of thing. But even with speedometers, drift is always an issue, so any inertial tracking system has to have some way of removing the drift, which means you have to have some non-drifting tracking system on top of it, which on the surface is generally GPS. But for underground cases, if you have another non-drifting tracking in addition to the inertial tracking is really just there to improve accuracy. But the good thing about inertial tracking is there's very little hardware and processing required. So MEMS-based inertial measurement units can be as low as $60. Very good ones are in the range of a few thousand, but overall it's relatively cheap. So for megahertz signal type tracking, very dense RFID tag setups have had accuracies under a meter. However, these had very large numbers of RFID transmitters. Systems using like Wi-Fi hotspots or Zigbee, for example, with more realistically spaced out transmitter distances, get accuracies to within a few meters. But as we saw with the project in the class, these often end up requiring quite a few transmitters. So at least every tens to maybe every 100 meters, you need a transmitter. And the signals also don't really play nicely inside of mine shafts and the sort of environments that you would have in an underground mine. So in the end, for a large mine, you end up needing quite a lot of transmitters. Mapping results, I haven't seen anything actually with actually doing position tracking from mining, but some results have shown that by having an inertial measurement unit and a 3D laser scanner on a vehicle, it can produce a map within a meter of accuracy of the area it traveled in. However, this was done offline after the data was collection. So in theory, if the map producing could be done online on the fly, it could provide very accurate position location for the vehicle. However, major drawback to this is that 3D laser scanners are very expensive, and there's a big computational load for this. So while inertial tracking can be done with a very, very cheap embedded system type computer, laser scanning might require a more powerful PC. And lastly, magnetic tracking. I've seen very little results on this, but the results I saw were interesting. Basically, there was 4 dipoles, so effectively like bar magnets, fields that were generated on the surface, and tracking was done below that. And they had an accuracy of within 10 to 50 meters on average with no drift. So it was working very much like GPS style, where you had 4 field generators and the fields were measured. But the paper didn't mention, though, that with a dipole field, the field strength drops off with the cube of distance. So you'd need either very large fields generated or quite a large amount of fields to cover an entire mine site. So you'd have very, very strong fields near the generator, and then it would quickly drop off, and somewhere between those distances would be like a sweet spot where you could actually measure the field. But overall, it doesn't strike me as something that would be realistically useful. So, having seen the competition, I'll just explain really why we want to mimic GPS. So, when you say GPS-like system, really what you're saying is that you have a small number of sort of set units that are broadcasting some signal, and to track your position and or orientation, you're just reading that signal and doing some computations on it that allow you to get your position. So for GPS, really what they're transmitting is they're giving the receiver time of flight, so it knows how long the signal took to travel from the satellites to itself, and from that it can do some triangulation basically to figure out its position. So it's kind of like intersecting spheres around the satellites. But overall, GPS is accurate, it's reliable, and it generally has a wide area coverage. So for the Earth GPS system, for example, I believe there's 28 satellites that cover the entire globe. And so long as the satellites are working, it's a pretty reliable system. So because you have so few satellites, you can put a lot of effort into increasing the satellite reliability and the satellite accuracy. And then that allows you to have cheaper receivers on the receiving side. And so really this is the kind of system you'd want for something like a mine, where you have a small number of sort of more complicated devices, so the transmitters, that allow very cheap receivers to get position data from them. So the solution that I looked at, proposed by Baiden, uses very low frequency transmitters, which are labeled by the XYZ coordinates on this figure that's from his patent. So the very low frequency signals are able to penetrate the rock, and the transmitters and the receivers are synced to a common clock, so they all know they all have the same time scale. And by having the same common and accurate time, they're able to measure the phase shift of the signal that's transmitted. So by measuring the phase shift, they're able to get the distance to the transmitters. So the math behind this is really quite simple. There's really 2 key equations. So there's the distance calculated from the phase shift, which is wavelength times meters over 360 degrees times the phase shift angle in degrees, and that gives you your distance to the transmitter from the phase shift. And you can also calculate the distance to the transmitter just from triangulation, knowing your position and knowing the transmitter position. So by measuring 3 or more distances via phase shift, you can solve the triangulated distances as a system of equations for the x, y, and z coordinates of the receiver. And this is what I did in the simulation. It's a little more complicated than that, how it's actually implemented. I used least squares estimation to minimize the errors in the position, but this is the basics of the idea. So the first key thing sort of I'll go into about the physical aspects of this is using the very low frequency signal. This is really what enables this technology, in theory, to work. So the figure on the right here is conductivity of some common rocks, and the figure on the left shows the skin depth, which is roughly how far a signal will penetrate into a material of that conductivity. So the conductivity scales on these plots are both the same. And the skin depth plot is at 5 kilohertz, so that's well within very low frequency, which is in the 3 to 30 kilohertz range. So you can see towards the right side of the skin depth plot, you start getting skin depths in the 500 to maybe a few kilometers range, which is really something that would actually allow you to have sort of a GPS-like navigation underground. So from the conductivity figure, you can see that this is actually realistically attainable, those levels of conductivity for a lot of types of rock. However, many types of rock, especially sort of clays and weathered rocks, it wouldn't really work for. And you can also see that salt water and fresh water are quite conductive, which shows that any kind of mining situation where the rock is heavily inundated with water would greatly increase the conductivity, which would greatly reduce the range that the signals can be measured at. And so this is just sort of demonstrating what phase shift is. So the transmitters are stationary, so they could have an atomic clock just attached right to them. And so if your transmitted signal is a sine wave, at the receiving end, it's also got an accurate clock, which at some point would have to be synced with the atomic clock. And so it's getting the sine wave, and it can measure the phase shift because it knows when the signal started. So for my simulation setup, I just had the vehicle traveling in a straight line, and position was calculated every second. So it was capturing data, simulated antenna data, at a rate of 40,000 samples per second, but then every second it would take all that accumulated data and calculate the phase shift and calculate the position from it. So I also assumed that signal attenuation was caused entirely by rock conductivity, so I sort of ignored reflections within the rock. I assumed the rock was homogeneous, and yeah, it didn't account for any variations in attenuation or that kind of thing. And the receiver noise, the antenna sampling rate, and clock noise are really just all things that I chose as simulation parameters. So the first results I have are just the ideal results, so no receiver noise. And for all the simulation setups I did, I had 6 antennas which were at 500 meters away in each direction, and I set the rock conductivity at 0.1 millisiemens, which is sort of on the low end of conductivity from the figure from the geology textbook that I had. So in this plot, the vehicle I had moving at 1 meter per second along the x-axis for 50 seconds. So as you can see, with no receiver noise, it was able to actually track the data perfectly as you'd expect. So then I started adding in receiver noise to the system. So with low noise, so 0.01 volts, and this is with the signal being 1 volt at the antenna. So at this conductivity at 500 meters, it would have attenuated by about half. So it would be measured at 0.5 volts. So with this system, the error sort of rose and then reached a steady state value of about 10 meters after about 250 seconds into the simulation. So really this is the best result I had, and it shows that even with a pretty low noise and a good rock conductivity and the very ideal simulator results that I had, the accuracy still wasn't great. So in a real world situation, there'd likely be other sources of noise. There'd be more clock drift. The conductivity could be a lot worse. So it really shows that even in very ideal situations, the accuracy of this system in a perfect sort of simulator world is not particularly great. 10 meters is not really something you might consider good enough for knowing where you are in a mine. It could very easily put a vehicle inside of a wall instead of on a path. So I continued testing it. I raised the noise again and left the conductivity the same. So increasing the noise to 0.1 volts. The position error just grew linearly with time. It didn't show any signs of stopping at this point, at the 100-second mark. Similarly, lowering the noise again to the level it was when we had better results, but raising the conductivity, you get a similar situation where the position error just keeps growing and growing and doesn't really show any time of stopping. And so with these position errors, it's really useless for anything. You know, a few hundred meters of position error isn't telling you a whole lot about where a vehicle is. So, and with this conductivity, it increased by 10 times from the good simulation to this one, which isn't really entirely unrealistic. Conductivity of rock can change with water flow and that kind of thing, and different types of rocks have much different conductivities. So for the system to be robust, it'd really have to work over, ideally, a relatively large range of conductivity. Otherwise, it would only work in sort of the specific mines that have the correct type of non-conducting rock for the signal to propagate. So, having seen that, there's something I also should mention, which is that the whole idea is sort of based on having very low frequency transmitters that are embedded in the rock and basically act as a point source. So we're assuming for the simulations that the position of the transmitters is known and that it's a point. But very low frequency transmitters are actually usually very large. I mean, they can be up in the range of a few kilometers, because the wavelengths of the signals are in the kilometers. So the picture I have here is actually a fairly small, very low frequency transmitter. Receivers can be made very small. So you can have portable receivers, but transmitters themselves I haven't seen much. And even for things like submarines, which use very low frequency data communication, the communication will only be one way. They'll have a receiver on the submarine that receives signals, but they'll use some other type of communication to send. So it's possible that it might not be feasible to even make a small enough antenna for the system to work at very low frequencies. And if you can't have the transmitted signals at very low frequencies, really the whole thing won't work. The signals will attenuate much too quickly to get a useful range. So in conclusion, really, it might work in sort of ideal conditions, but it requires a very good signal-to-noise ratio, and much more importantly than that, you have to have very good rock conductivity. So you're looking at about the lowest end of conductivity of rocks that exist for it to work. So it'd be very limited in the mines that it could actually be implemented in, and if anything were to change with the rocks, so fractures or seawater gets into them, anything like that, it would really just fail to work. And there's a lot of sources of noise and that sort of thing that I ignored for this. I didn't actually test clock drift, and there's also sources of natural, very low frequency noise. So lightning, for example, has a lot of low frequency noise that it generates, and there's also low frequency or very low frequency signals that are generated for other tracking systems. So really, it's not overly promising that this is a realistic system. And also very sort of peculiarly is there's very little results seen from Baiden, the man who patented the idea originally. In 2009, when he first released information about this, he said that he had some preliminary results, but I haven't seen anything from him about this system since then. But that's all for my presentation. I hope you found it interesting, and I hope you learned something. So thanks for listening.